Okay, all right. So we're back here. So just in time for the new topic. So the practical op-amps. So this is what we talked about previous time in the previous lecture. So these are just you don't apply the golden rule. Okay, so these are all practical op-amps have this constraint. So the next set of imperfections, these are really imperfections. They are nonlinear imperfections. The first set is, these are still linear correction. The finite time bandwidth, gain bandwidth product, these are still more or less in the linear regimes. So the next set of constraint is nonlinear. It's really, ideally, if you can eliminate it, that will make life so much easier. But as we will, towards the end of the lecture, show you the inside of the op-amp, then you will know where all these non-idealities come from. Okay, so we're going to go through. There are slew rate, there are swing limit, there are offset voltage. We won't be talking about noise and distortion. We will talk about the effect of input bias. Okay, question? Yes. This? Okay, all right. Okay. All right. Okay, so I'm trying the new system also. Anytime you see anything, let me know. So first thing is offset voltage. The first time, I believe you have already tried op-amp in 16 experiments, right? So you always need to apply an offset voltage. So what does offset voltage mean? So for op-amp, you have two input terminals here, okay, 1 and 2, and there's an output voltage. The ideal op-amp transfer curve is like this. So this will be ideal op-amp transfer curve. This is the input voltage, so this is basically equal to V1 minus V2. So this is VID, is the difference of these two voltage. Actually, it's actually V2 over V1. That's minus terminal is V1. So this is V2 minus V1. Note that the units is in millivolts. So these are minute differences. These two terminals, we say they are virtually connected. They are actually not, but they are separated in millivolt, like a few millivolts. Whereas the output voltage, VO here, this output voltage measures in volt. So these are huge signals. And you can calculate the gain. The gain here would be something like 2 millivolts give you 10 volts output. So this will be like 5,000 open loop gain in this plot. Now, in real op-amp, however, this curve, where they happen exactly, kind of vary from chip to chip. Every time you get a chip, it could be here, it could be here, it could be here, and in this textbook example, it is here. So it has a 5 millivolt fixed offset. So in other words, your output will be equivalent to something like you have kind of attached offset voltage source in series with one of the terminals. And this comes from the mismatch of the transistors inside the op-amp. So at least towards the end of the semester, I'll show you exactly where this is. All right. For the time being, think of it as kind of unavoidable non-ideality. So all op-amps you buy, you get, they come in all kinds of forms. Some are in this called dual inline package, deep package, dual inline package, because it has two lines. Or you get these TO can, a round type of package. They come in all kinds of forms. Actually, you can choose which form you get. And there's always two offset terminals. There's always offset terminal here. So if you look at the connections, V plus, this goes to power supply. So this could go to, say, plus 15 volt if your power supply is 15 volt. V minus go to minus 15 volt, basically the most negative voltage in the systems. And then there are two inputs. So there are inverting input, there are non-inverting input. So this is where you apply V minus. This is where you apply V plus, okay? And output is VO. This NC means not connected, so there's just open terminal, nothing there. So these two offset now is intended for you to use something like this. You will connect these two terminals to V minus through a variable resistor. So this is a potential meter. And there is a suggested value. Let's say, this is maybe 10 kilo ohm, total 10 kilo ohm potentiometer that you use. And the middle terminal is connected to V minus. So if this terminal is exactly in the middle, you'll say, well, the left part is 20 kilo ohm, the right part is 20 kilo ohm. Okay, so in the case of no non-ideality, then you will have this R left equal to R right. Okay. Now, in the case of the offset shown in the previous slide, you will need to send slightly more current in one of the biasing circuits. So you will move this slightly to one side to neutralize the offset. How do we know which side to move? Well, you find that out experimentally. You put both, you go back here, you put both input ground, and you measure your output voltage. And in the meantime, you connect your now offset to your V minus. You just turn the dial until your output voltage goes to 0. So you kind of force your transfer curve wherever they are. You force them back to the line that passed through origin. Okay. So operational. This is basically operational. That's the deeper theory. We will need to look inside the transistor, which will happen towards the end. Okay. And you trace the same output. It's same number of output pins, so it's always there. Okay, so this is what you will find out in the lab. The next non-ideality, it's not non-ideality. It's really just a practical requirements. We said there's no current going into the terminal, right? In the ideal amplifier, we said I equal to 0. Both of them have infinite input impedance. In real op-amp, this is true for some of the op-amps, so this is where it gets confusing. So for MOS op-amp, we're going to talk in detail MOS. MOS stands for metal oxide semiconductor. That's the dominant transistor we use today. In MOS op-amp, well, this I input is kind of equal to 0. Let's call this IB. Okay. In another type of technology called bipolar junction technology, bipolar junction transistor, BJT, bipolar junction transistor. In this type of op-amp, well, you need a bias current, and it is not 0. So in this case, IB is not 0. They are not big, they are very small. They're probably smaller than your signal current, but they are small. Nevertheless, they have impact that you can see and impact the performance of your circuit functions. So how big are they? Well, you can see these in the specifications at the end. We'll show you that. But they are kind of, well, think of it small, 100 nanoamp. 100 nanoamp is very small, 10 to the minus 9 times 100, so 10 to the minus 7. But we'll show you what's the impact. And they are not the same. When they are not 0, IB1 minus IB2, the difference between two of them we call offset. So this offset is not 0 either. These are about 10 times smaller. So they are matched to within 10%, but they are not 0. Okay. So for now, remember kind of each of them is about 100 nanoamp and difference 10 nanoamp. So what are the impact? So here is the impact. Let's say we go back and see this inverting amplifier. So now we add these bias current here. So we add IB1, IB2. If they are not 0, what happened? If we analyze the circuit, assume this is ideal other than the IB1, IB2 non-zero. Okay, the rest is ideal. And then you see, okay, so here is ground. So here, V minus is kind of also equal to V plus. That's equal to 0. And so the current flowing through R1 is 0 because it's 0 on both sides. So I1 is equal to 0. Whoops, that's so I1 is equal to 0. Now this terminal is 0, but IB1 is not 0. So that means the current must be supplying through this terminal here, right? So I2 is equal to IB1, which is not 0 now, 100 nanoamp. And your output voltage is equal to V minus plus the voltage drop across R2, which is I2 R2. Now this becomes IB1 times R2. Okay, so this is 100 nanoamp. We say this is roughly 100 nanoamp. Well, depends how big R2 is. R2, if you have a mega ohm, for example, then this product is that gives you roughly 0.1 volt, 100 millivolt, 0.1 volt. 0.1 volt is not insignificant. This is where both of your input are grounded. You are not applying any signal. This is just caused by bias current in the circuit. Okay, so obviously you want to minimize that. It turns out it's not possible to completely eliminate it, so you can minimize it. So how do you minimize it? You minimize it by kind of add a feedback effect. So you add a resistor in this path here. So in other words, we add this R3 here. So this is a new element we added to the system, okay? And this system we'll see how it helps us moderate this effect. So now let's look at this here. So we still assume the rest of the op-amp is ideal. Then the voltage here, so V plus here, is equal to, the current. So now there is current going into the terminal. This is 0, so this is equal to 0 minus IB2 times R3. Okay, so it's no longer 0 due to the finite bias current we have to send into the terminals. So V minus, we say, it's equal to V plus. So it's the same, minus IB2 times R3, right? And so we know the voltage here. Then we know I1, okay? So I1 is basically equal to the terminal voltage difference, 0 minus V minus divided by R1. So this is equal to IB2 times R3 over R1, right? So this current is going to flow in here, and there is current also flowing here, IB1 flowing here. So part of the current flowing here and other part of the current will flow out. So the current flowing out, or you can sort of think of it differently. There are current flowing on this side. So there's a Kirchhoff current law here. So then we can say I2 here, that's this current I2. I2 will be equal to IB1 minus I1, okay? So this will be I2. And now VO is going to be equal to this voltage here. It's V, this is a V minus terminal, okay? And then plus the voltage drop. So it's always, you mark sign. The current always flows from plus to negative terminal. In the convention, the real sign depends on the polarity of the answer you get. So this is adding I2 times R2, okay? So you can add this up. So this is minus here, minus IB2 times R3, that's V minus, plus IB1, okay? IB1 minus I1 minus IB2 times R3 divided by R1 and times R2. Okay. So now it's a little bit algebra that you have to go through. So this is, if we extract IB here, so this is IB, this becomes R2, so R2, that's this term here, minus R3, R2 divided by R1 minus R3, okay? So you clean up this term. This is IB2 times R2 minus R3, and this will be R2 over R1 plus 1. Okay, long algebra, but so here is this. Here we kind of assume IB1 equal to IB2 here. Okay, so we say IB1 is roughly equal to IB2. So if we set this term equal to 0, which means R3 is equal to R2 divided by R2 over R1 plus 1. And you'll find this is actually equal to R1, R2, R1 plus R2. So that's the parallel combination of R1 and R2. So you recognize this R3, the best value for R3 is actually parallel combination of R1 and R2. Okay, all right. Now, once you understand why this is doing, you'll say, oh, that makes sense. If you insert this value in here, you kind of canceling out the dominant effect of these finite bias current that you need to send to the terminals. Okay, so in this case, well, it seems if we make this choice, then this approaches 0. However, they are not really 0, and you will trace that. You remember that IB1 actually is equal to IB minus, say, there's an offset. Let's say plus offset divided by 2. IB2 is equal to IB minus offset. So now we keep track of their difference, 10% difference. And then you plug it back into the original equation here without assuming IB1 equal to IB2, okay? I'll skip that part of the math. And if you substitute in there, you will get now your offset voltage, VO, is equal to I offset times R2, okay? So there's still finite offset value. But if you recall, in the earlier example, if we don't do anything, this is equal to IB times R2. If we do this trick, it's IOS times R2. So we reduce it by about 10 times since IOS offset is roughly 10% of IB. So we reduce that output voltage by 10 times. So that's quite significant. Okay. So this is the type of trick we will need to use to mitigate each of these practical aspects of the op-amp. All right. So the circuit element is, the algebra is kind of messy, but the principle should be quite straightforward. Yep.
And basically the only thing we can tweak is those resistances, right?
Yeah. That's right. Unless you do something much more sophisticated. This is an easy fix. All right, okay. So other nonlinear effects, output saturation. So if you have touched any circuits, you all know signals saturate. And in some cases, like digital circuit, we take advantage of that. We make them saturate, so they become bit 1. If they go to the bottom, they become bit 0. In the LTI system, linear time invariant system, we want to preserve their analog nature. And so if you have an input that's sinusoid, okay, your output, you want them to be sinusoid. But if your power supply voltage is finite, so we said usually we need to apply, bias plus 15 volt to the op-amp and apply minus 15 volt to the op-amp. And so in this case, there is a finite drop. The highest voltage you have here cannot be 15 volts, okay? In this example is a 2 volt drop, but this precise amount of drop depends on the implementation, depends on what kind of transistors we choose in this op-amp. So it's typically 1 to 2 volt. So this is about 1 to 2 volt below the maximum voltage, which is power supply voltage. Likewise, in the negative side, it's also 1 to 2 volts above this limit. And if you exceed that, if your open loop gain, like in this case, you have a gain of 9, and you expect your output voltage to be 15 volts, and you hit that maximum saturation, your signal will be basically chopped off. So it will be clamped. We call this kind of clamped by the power supply voltage. So what do we do? Well, you need to ensure your input signal. So you usually set your VI magnitude to be smaller than some maximum amount. You don't exceed that. When you exceeded that, you know your signal is going to become nonlinear. If you're playing a music, your amplifier starts to go nonlinear, you start to hear new frequencies. So you start to hear sounds that shouldn't be there, and usually that's not pleasant. So usually you want to prevent this from happening. Alternatively, if you really need this big output power, you should choose an op-amp that can take higher power supply voltage. Then your clamp voltage will be higher. Okay. Right? So these are just practical constraints. Okay. Next, slew rate. Slew rate is a concept that if you want to go, say, like in the previous examples, your input voltage, you go from a step function, and your output voltage, let's say you want to go from 0 to 10 volt, okay? Now, you don't expect your output voltage to follow your input voltage. There are actually 2 limits. One, we all know amplifier has a bandwidth. So a sharp transition like this is like bandwidth is like infinity. So we don't expect the output to faithfully reproduce this sharp edge if it has a finite bandwidth. But slew rate is something different. Slew rate is like, take an analogy of a car, 0 to 60. So, it takes, used to take 5 seconds. Now with electric cars, you can go in 3 seconds. But it takes finite time to bring the car. There's a momentum. So similar to cars, the mechanical energy, there's a momentum. It takes time for the velocity to reach up to 60. Or if you want to think about voltage to really say water level, if you are filling a tank, okay, so here is your output voltage, V out. But you started with very little water here. Slew rate is kind of like, well, the maximum faucet you have, the maximum output current you have is like a faucet. So you run your faucet, try to fill up your tank up to the steady state level, V out here. It takes time for the liquid to fill up the tank. So that's the slew rate means. And if you go to the specification, you will see the slew rate typically specified in volt per microsecond. These are the typical number. Let's say if your slew rate equals 1 volt per microsecond, this is from the spec, okay? When you buy the op-amp, you will know what you are buying. If this is the case, your output voltage is 10 volt, okay? And you are starting from 0 volt to 10 volt. Then your slew rate, the time it takes for the ramping will be 10 volt divided by the slew rate. This will be 10 microsecond, okay? 10 microsecond. That's the fastest you can get to 10 volt. And this is just due to the finite output current in the op-amp. Okay. Questions? So don't expect your output to follow your input faithfully. Okay. Now we can go actually check. op-amp. You'll be given an op-amp in your lab, so you don't have to look at this eye chart. But I encourage you to do this. You go to TI.com. TI, Texas Instruments, is one of the 2 major companies that produce analog integrated circuits. You just, in the search bar, type op-amp. And you will see about 1,468 op-amps. These are that many op-amps there. So they are not 1, 2, 10 different type of animals. There are thousands of different animals. And if you go to a different company, their competitor, analog devices, ADI, so you can also check ADI. They have another thousands of op-amps. So quite a bit of choices. And what do you choose from? So they have this manual bar that you choose. You may not be able to see it here, but normally you choose like the starting one. Okay, what's your power supply voltage? Okay, V plus, V minus, you choose that. Then very high up, you choose your gain bandwidth product. Gain bandwidth product, okay. So this is listed here. This is a gain bandwidth product, so it is here. The unit, if you cannot read, the unit says megahertz here, and you see what you can find. There are 2 megahertz, 1 megahertz, 1 megahertz, and then there's this guy, 1,000 megahertz. So if you are working with a high-speed application, video signals, you probably want to look at this guy. 1,000 megahertz, 1 gigahertz gain bandwidth product, right? This can only give you so much. If you want to work with a full bandwidth of 2 megahertz, you run out of gain. Then you go to this guy with a higher gain bandwidth product. They don't come for free. If you keep checking the spec down the same row, you will see where you take a penalty. Maybe the power consumption is much higher. Usually it's not price. These 2 guys are all on the order of $1 per unit. Really cheap, so it's usually not the price. But you may pay a penalty in power consumption, okay? The next thing you choose is a slew rate. So here is a slew rate, usually the second thing you choose. So slew rate is here. This is slew rate. Indeed, it measures in volt per microsecond. Okay, so you see slew rate. They are roughly the same. Usually on the order of 1 volt, maybe 10 volt. And then there's this guy again, 8,000 volt per microsecond. So this is a fast guy. You can kind of get a sense. If you want something fast that can follow your input quickly, you probably want to do this guy. So what is it called? High-speed buffer, closed-loop buffer, high-speed closed-loop buffer. The next guy is also high. This is a high-speed buffer. So this kind of the name suggests how you're going to use this. So slew rate, very important, but it's in your choice of your starting components. Once you get it, then you just have fixed the bandwidth, gain bandwidth product to play with, and you are limited to whatever that op-amp's slew rate. Okay. So now here is an interesting question. If I have a step function, okay, if my input is as what I had before, I have a step function input, Vi versus time. Now, if I have a slew rate limit, we'll say we're going to have a finite slope reaching to the steady state value. So here is, if you solve your steady state circuit, you're going to get this steady state output. Now, because we have finite bandwidth, if you don't have slew rate limit, you're still going to see your bandwidth limit here. So how do we know what are we limited by? So we need to do a little bit analysis. What are we limited by? You check the slope. If the slope is exactly equal to the spec of the op-amp, you are limited by the slew rate. It's possible you are not limited by the slew rate, but rather you are limited by your bandwidth. So if you recall, I believe you all solved this problem. The bandwidth problem is more like RC limit. If you are charging a capacitor through a resistor, okay, so you are charging here. So if you have a step input response, your output will look like something like, this is your 1. And then you have 1 minus exponential. So this curve is like 1 minus exponential minus t over RC, right? So if you draw a line here, and if you draw the incept, this time is 1 over RC time, okay? So if your slope is less than, if you measure the slope, if your slope is less than your slew rate, then you are limited by bandwidth, okay? And it's coming from different origins. So if you want to solve this issue, you need to know which origin it came from, okay? So which means this has additional limit on how you use the op-amp. And you need to know this fundamental limit before you construct your circuit. So assuming your signal is Vi, which is equal to amplitude Vi at the frequency omega t, and then you calculate your maximum change. So your maximum change for this unity gain, this output is VO is equal to Vi basically. In this case, you can calculate the slope. The slope is basically dVi dt, and that's a derivative of sine. You get Vi times omega times cosine omega t. This cosine omega t is basically less or equal to 1. So the maximum value of your input, if it is a sinusoidal, so we are considering a sinusoidal input, your maximum slope at your output of the unity gain amplifier is going to be equal to Vi times omega. And usually we don't want our circuit to operate limited by slew rate. So this has to be smaller or equal to slew rate. So this places a limit on your amplitude or frequency. So the product of your input amplitude, so this is your input amplitude. And this is your operating frequency. The product of the two should be less than slew rate. And you either buy op-amp with sufficiently high slew rate, or else you should limit your input voltage. Your input voltage should not be exceeding the slew rate. So if you exceed your slew rate, this is an example where you exceeded your slew rate. So your input is a sinusoid. Ideally, if you have a unity gain, this is a unity feedback. You have unity gain amplifier, your output should be like this. But if you are slew rate limited, as you start to increase, your amplifier is running out of steam. So it can only do here. By the time you get here, your real output already start to change sign, so you start to reverse and work as hard as you can, so it kind of becoming a triangular wave. And the triangular wave is a huge distortion from the original sinusoidal wave. So this is where your circuit, your linear circuit completely fails. This is a case we want to avoid. Okay. So the key takeaway is choose an op-amp that fits your application. There are so many you can choose from, and almost always, unless you are really at the cutting edge, dealing with signal much faster than anybody else, usually you find a selection of a component you can use. And then you find your circuit and apply, remember the nulling to make sure you operate passing the origin, and you take care of your bias current, or you choose a MOS input stage which doesn't have bias current. Okay, all right. So you know more about op-amp than you need to. Until you start doing experiments, then all this becomes useful. Okay, any other questions? So we're going to, this will conclude our module 1 here. And the next topic will be module 2. Yes, questions? Yes. So in your lab, you'll be given an op-amp. You'll not be bringing your own op-amp, and you should either be given a part number, and with part number you can go online and look at their origin. All the specs are online, so you will know precisely the specification of the chip you have. The slew rate, if you look, here is kind of a summary table. If you go to the individual items, you will say slew rate, typical value, 1 volt per microsecond, maximum value, 2 volt per microsecond, minimum value. So there's a range there. It's not a same fixed constant for different chips. There's a range. Yes?
Can you explain again how the slew rate is related to the bandwidth?
So slew rate is not related to the bandwidth. When you think slew rate, think the op-amp just have a finite current drive capability. In order to reach the output voltage, you think of it as voltage. Think of voltage as the height of the water level in a tank. So you want to reach a certain output voltage, but it takes time to fill the tank, because when you turn on your faucet, it's like you turn it to the max. The current supplying element inside the op-amp are working as hard as it can, and it's already maxed out, and you still take finite time to fill up the voltage.
And why is it originally here that the bandwidth is infinity for a vertical slope?
So why is the square wave voltage bandwidth infinite? If you think of the simplest answer, most rigorous answer is when you take 120, you take a Fourier transform, then you know all the frequency component of function like this, and the frequency component goes to infinity. Let's look at the simpler way to look at this. So we'll go back to our RC circuit here. So we say, well, if we have a RC circuit and we apply if we apply step function here, and the output is going to approaching the steady state value, but with the exponential function. So it goes up, it goes up exponentially, but eventually approaching this here. And we said roughly this is RC time, so 1 over RC, that's this time here. And if you have faster circuit, you have smaller capacitance. So if you imagine your capacitance goes to 0, then your RC, so sorry, this is RC time, not 1 over RC. So this is RC time here. So if your capacitance goes to 0, then you kind of going up faster and faster. And so this is a faster circuit. So you have broader and broader frequency component. And if you have absolutely sharp, then it's infinite frequency. So nothing is really of infinitely sharp. This mathematical function in real case, it always have finite slope, ever so slightly finite slope. Any other question? Yeah.